Hi everyone, the topic of my presentation today is active current source gate driver for dynamic voltage balancing in series connected GaN HEMTs. My name is Zhengda Zhang, a newly graduated PhD student from Arizona State University, and my advisor is Professor Qin Lei. Gallium nitride devices can improve the power density. This figure shows the material properties of silicon carbide, and gallium nitride devices. So we can see gallium nitride devices has a lot of good properties. Wide bandgap devices can reduce the power loss and increase the operating frequency. In that way, we can significantly increase the power density of the converters. The benefits of gallium nitride devices compared with silicon carbide are summarized here. Gallium nitride devices has lower junction capacitance, zero reverse recovery loss, lower gate charge, it is better for higher frequency applications, and it has lower substrate costs. This is the structure of infinite GaN high mobility electron transistor. The major drawback for gallium nitride devices is the lateral structure, which limits the voltage rating below 650 watt for the commercial GaN power devices. So it is not suitable for future 800 watt DC-link or even above EV applications. To sustain higher DC-link voltage, two strategies can be utilized. So the first strategy is the multi-level converter. The pros for the multi-level converter includes a lower DVT, lower EMI, and a lower output harmonics. The cons include the complicated hardware structure as well as the complicated control. So this topology is actually the active neutral point clamp ANPC converter, which is widely used in commercial PV inverters. The second strategy is the series connected switch strategy. The pros for this strategy include the simpler hardware structure and simpler control. The cons include the unbalanced dynamic voltage sharing, which may cause the overvoltage for the low voltage rating individual device. So when the lower arm switch are turned off, the two VDS may not be equal, which can be caused by the gate-driven variation, the device parameter variation, as well as the device to ground displacement current. So the last factor is considered to be the major cost. So we can see our major challenge is the dynamic voltage balancing control for series connected fast switch gallium nitride devices. Next, let's look at the root cause for the voltage imbalance in soft turn-off. So the soft turn-off is defined as here. So load current is assisting the charging and discharging of device junction capacitance. So in this schematic, we can see we have the parasitic capacitance, both the gate to ground parasitic capacitance as well as the drain to ground parasitic capacitance. So the origin of the parasitic capacitance include the device to sink, the isolation capacitance for DC-DC and gate drivers, as well as the PCB interlayer capacitance. Next, let's look at the gate current of S3. So the gate current of S3 equals I of S3 plus IP3. So IP3 is the gate to ground displacement current. And the gate current of S4 only equals I of S4 because the gate to ground displacement current is almost zero because there is no high DVT between the gate and the ground. Next, let's look at the drain current of S3. The drain current of S3 equals this equation, and the drain current of S4 equals this equation. We can see the IP5, IP6, they are the drain to ground displacement current. So based on these equations, we can see S3 has both higher gate current and higher drain current than S4. So we know based on these two equations, the device drain to source DVT can be determined by either gate current or drain current. Regardless, S3 will exhibit higher DVT than S4, which will cause the voltage imbalance. For gallium nitride devices, DVT is typically determined by drain current due to the small input capacitance. The gate can be discharged below the threshold very quickly. Next, let's look at the root cause for the voltage imbalance in hard turn-off scenario. So the hard turn-off is defined as the load current is not assisting the charging and discharging of the device junction capacitance. So the drain current of S3 can be expressed by this equation, and the drain current of S4 can be expressed by this equation. Again, both IP5 and IP6 are drain to ground displacement current. So we can see S3 has higher drain current than S4. And based on these equations, since S3 and S4 are already at the gate off state, drain to source DVDT will be determined by the drain current. So S3 will exhibit higher DVDT than S4, which will cause the voltage imbalance. So this scenario is also called the series connected body diode or diode-like scenario. So basically, we have two methods to address this. The passive method is to add additional capacitive compensation, which is tedious and lossy. And the active method is to trigger the gate during the DVT transit, which requires very high accuracy. So then current source gate driver CSGD is preferred because current source gate driver directly controls the device gate current, so it is more accurate and flexible. Next is the proposed voltage balancing scheme in soft turn-off scenario. First, let's look at the simplified schematic of the proposed current source gate driver. The key features are summarized here. First, we have controllable current sources, the turn-on gate current, the turn-off gate current source, the compensation gate current source, which direction is opposite from the turn-off gate current source. And we also have an on-state current source, which is only used for GaN gate injection transistor gate. Second, the steady state, off-state, or on-state voltage clamping, V off or V on for P gate GaN, or I on state for GaN GIT. Because of the current source gate driver, we don't have the voltage, the steady state voltage, so we need to do the steady state voltage clamping for the device. Next, the multi-level gate current control capability. So for each turn on and turn off and compensation gate current source, we can do the multi-level gate current control. Last but not least, the gate current is directly controlled, so we can achieve more accurate control of the DVT starting timing, as well as the slew rate. The employment of additional ICOM improves the gate current regulation accuracy and flexibility. So without the active gate current control, we can see the turn-off timing of the two devices is the same. And because of the difference in the drain current, the top sitting switch S3 will have a higher DVT and will eventually have higher voltage. So with the active gate current control, we basically add a compensation current. We have the pulse width as Tcom and amplitude as Icom. So we basically reduce the total turn-off gate current. So turn-off timing for the top sitting switch S3 is delayed by a certain time. In that way, we achieve the balanced voltage sharing. So the active gate current control with CSGD, basically we use DVT starting timing difference to compensate for the slew rate difference. And we have two control freedoms, which is ICOM and TCOM. It is basically the compensation gate charge control. Next, let's look at the proposed voltage balancing control in hard turn-off scenario. So without the active gate current control, we can see during the complementary switch hard turn-on transit, DVT occurs because of the difference in the drain current. The top sitting switch S3 will have higher DVT, so eventually it will have higher drain to source voltage. And with active gate current control, we can see we trigger the gate of S3 during the DVT transit. So we basically control the slew rate of the two devices, and eventually we achieve a balanced voltage sharing. So the equivalent circuit when the VGS of S3 is just above threshold is shown here. Since the gate of S3 is triggered again, so it should be regarded as a large resistor rather than RDS on, or and a junction capacitor. So we basically change the impedance. The equivalent circuit when VGS of F3 is below the threshold is shown here. So when the threshold drops below, or when the VGS voltage drops below the threshold, the device becomes a junction capacitor again. It should be mentioned here, a large I0 is used to reduce the rising time delay, and a smaller ICOM should be used here to improve the accuracy. So because we use a multi-level current source, so we have such capability. After that, a negative voltage clamping is used to safely turn off S3. So again, we have two control freedom at the ICOM and the TCOM. It is basically a compensation gate charge control. So basically, this scheme is active DVDT control with the current source control. We trigger the gate during the DVDT transit to reduce the device impedance. Although the gate of S3 is triggered, the dislink shoot-through will not occur because S4 is always at the gate off state. Next is the operating principles. Let's look at the hardware structure. The key features are summarized here. First, the current mirrors are utilized as the fast responded current sources. Here, we have 4 sets of current sources. Second, the parallel current mirrors can provide multi-level gate current. Third, the active negative voltage clamping is employed to guarantee the secure turn-off, which is shown here. Fourth, the RC voltage divider network is used to sense the off-state VDS. So we sense the steady state off-state voltage. So it is very robust compared with sensing the transient VDS voltage. Next, the window comparator is used to improve the control robustness because the window comparator has 2 thresholds. So whenever the sensed voltage is within the 2 threshold, we do not do any action for the control. So it is very robust. The TVS diode is used to prevent the device over voltage breakdown during the first few switching cycles. TVS diode is shown here as D3. Last but not least, all secondary components sit on the main switch source ground, and no other isolation is needed. It should be mentioned here, the current mirrors can be integrated into a small driver chip in the future, which will improve the power density of the whole gate driver. And in this method, we utilize the digital control to simplify the structure. If the analog control is used, the D2A or analog controller will be required. Next is our control algorithm. After the initialization, we need to check the direction of the load current. If the load current is in the same direction with the junction capacitance charging and discharging, it belongs to the soft turn-off scenario. Then we need to implement the active gate current control at the turn-off transit. Otherwise, it belongs to the hard turn-off scenario. We need to implement the active gate current control at the turn-on transit. And then we need to do the active tuning of TCOM and ICOM. For the active tuning of TCOM and ICOM, when the counter equals 1, we first do the active tuning of TCOM. And once the active tuning of TCOM finish, we increase the counter. When the counter equals 6, we do the active tuning of ICOM. So it should be mentioned that here N, which is the counter's number, is selected to be 6 in this study for balancing the transient response and the steady state error. It is not necessary to be 6. Next is our experimental verification. First, let's look at the setup. So for the soft turn-off, we parallel the air core inductor with the upper arm device, and the lower arm devices is regarded as the device under test. And for the hard turn-off, we parallel the air core inductor with the lower arm devices. Infineon 600 volt 7 10 milliohm GaN devices is selected as the main switch. For the first prototype, we have a large current mirror daughter board on the primary side, and we have our isolation transformer, and we also have our current mirror circuits for the secondary side. The drawback for this prototype is the current mirror transient is limited by the transformer leakage inductance because the IDT should be smaller than the power supply voltage. So we changed to our prototype 2. For prototype 2, we put all the current mirror circuits on the secondary side. Because of the very small stray inductance in the gate loop, the current mirror output DIDT can exceed 300 milliamp per nanosecond, which is very, very fast. Next is the demonstration of our prototype.
These two prototypes are the multiple pulse testers with the series connected GaN devices. For the main devices, we use Infineon GaN device. So this is a prototype 1. So the first version, we have the primary side current mirror daughter board, we have the isolation transformer, and we also have the secondary side current mirror circuits, which is located on the bottom of this motherboard. The drawback of this prototype is because of the leakage inductance of the transformer, the output current speed from the primary side current mirror daughter board is limited. To solve this problem, we directly put all the current mirror circuits on the secondary side of the gate driver. In that way, we can have very high speed output current for the gate. And we can see this part are the current mirror circuits for the secondary side. Okay. Meanwhile, we can see this is our VDS sensing circuit, which is used for the closed loop control. And this is our comparators, and this is our digital isolators. So the power density of this prototype is not optimized, which will be invested in the future study.
Okay, the next part is the validation. First, let's look at the soft turn-off scenario. The DVT is determined by the gate current. As we mentioned before, the GaN devices, the DVT should be limited by the drain current, but we manually add 10 picofarad extra Miller capacitance to mimic the high current rating power modules or slower device. So we can see without the active gate current control, we will have significantly voltage imbalance. After the active gate current control, we will have very balanced voltage sharing. So by actively controlling the gate current of S3, the DVT starting timing and slew rate are adjusted, so we can achieve well-balanced voltage sharing. Next is the validation for the soft turn-off scenario, but the DVT is determined by the drain current. This time we remove the extra Miller capacitance. So we can see without the active gate current control, the DVT is significantly different. So we have a very imbalanced voltage sharing. But with the active gate current control, we eventually achieve very balanced voltage sharing. So by actively controlling the gate current of S3, the DVT starting timing is adjusted. So well-balanced voltage sharing. Next is the validation for hard turn-off scenario. Without the active gate current control, we can see we have unbalanced voltage sharing. And after implementing the active gate current control, we can achieve well-balanced voltage sharing in the end. By actively controlling the gate current of S3, the DVT slew rate is adjusted, and we can achieve well-balanced voltage sharing. Next is the validation. We conducted the multiple pulse test at 800 volt this link. This is for soft turn-off scenario. We can see without the active gate current control, we have severe voltage imbalance for every pulses. Because we have the TPS diode will sustain the voltage imbalance, the over voltage energy. So we can see when the pulse goes on and on, we will see the slope becomes severe, more severe. This is caused by the reduced impedance of the TPS diode. If no active gate current control is implemented, the TPS diode can be damaged due to excessive loss. So after implement the active gate current control, we can see it is very flat. The VDS voltage is very flat, which implies the TPS diode is not in the breakdown region. So well-balanced voltage sharing is achieved with the proposed strategy in full load range. The TPS diode is only kicking for the first few pulses, and the dissipated loss is negligible. Next is the validation multiple pulse test for the hard turn-off scenario under the 800 watt dislink voltage. And it is very similar to the soft turn-off scenario. We can see without the active gate current control, The TVS diode will sustain the overvoltage energy, so the slope becomes more severe. And after implementing the active gate current control, we can see after a few pulses, the well-balanced voltage sharing is achieved. So our conclusion is that the well-balanced voltage sharing is achieved with the proposed strategy in full load range. TVS diode is only kicking for the first few pulses, and the dissipated loss is neglected. Thank you very much. That's all I have. For more information, please check out our articles. We have 2 articles published in IEEE Open Journal of Power Electronics. Thanks again.